So let me quickly recap before we move on. So what is the idea? The idea is that we started with a latent variable model, okay, which is defined as the marginal over the joint distribution between the observed data variable and some unobserved latent variable. We wanted to find the parameters theta that would minimize the KL divergence between Px and P theta, and we saw that this is equivalent to maximizing the expected log likelihood. Okay. Now, because we do not know what the latent variable is, as I said, the goal here is to learn a distribution over the latent variable as well while we are learning the model parameters. So we called q of z given x as a density function over the latent variable z, to be precise, latent variable z given x. So now, as we saw in the introduction for the latent variable model, the latent variable exists for each of the x. So given a particular x, we have some value for the latent variable. We started with the log likelihood function that we would want to optimize, and we could not optimize this because we landed up having a log of an expectation that cannot be computed in practice. We used a Jensen's inequality to create a lower bound on the log likelihood that we would want to optimize. So now, instead of maximizing the log likelihood, we are maximizing a lower bound on the log likelihood, also called as elbow or evidence lower bound. Okay. Now this evidence lower bound is a function of two things. One, it is a function of the model parameters theta. It is also a function of the distribution or the density function that we have imposed on the latent variable. So we simultaneously have to find out the model parameters theta and also the density function over the latent variable. So in any latent variable model, we have to do two things, which is that we find out the model parameters theta and we find out a distribution on the latent variable as well. So this is the problem that we are going to solve. See, one question that one might have is that why is maximizing a lower bound on a function that we would want to maximize optimal? Now, it is not optimal, okay, they are different, but what can be shown is that optimizing this particular lower bound with a particular algorithm called the expectation-maximization algorithm, which we will see now, will guarantee that the likelihood function that we would want to optimize will never decrease by solving this particular problem. Okay. However, it cannot be guaranteed that optimizing the lower bound will ensure that we will reach the global optima for the likelihood function that we would want to optimize. However, under a latent variable model, we cannot optimize the log likelihood directly. So there is no other, we have to resort to optimizing a lower bound on it. Okay. But anyway, so the idea is that in every latent variable model, we would solve this optimization problem, which is maximizing the evidence lower bound or a lower bound on the log likelihood function. And where did this come from? This came from minimizing the KL divergence between Px and P theta. And while we are optimizing the evidence lower bound, the optimization is over two set of parameters, rather not parameters, two set of variables. One is the model parameter theta, the other is the distribution over the latent variable that we are trying to learn or impose. Okay. So this is the idea. Now let us look at an example from the classical machine learning community for this particular algorithm, and then we will extend this to deep generative models, which is VAEs and diffusion models. So again, I am reiterating, be it VAE or a diffusion model, all the latent variable models are based on this principle of elbow optimization. So this is called, let me write that down, the fundamental problem solved in any latent variable generative model is given below. Okay, this is called elbow maximization. Okay, which is find theta and q that would maximize the elbow, that maximizes the lower bound on the likelihood, which is also called the elbow. Maximizes the evidence lower bound, which is j theta of q. Okay, so this is the problem that we will be solving consistently in any latent variable model that we will be looking at in this course further. Okay, right. So the way we do it is very different in each of the model that we will see. So for instance, we solve it in a different way for in a VAE, we solve it in a slightly different way for a diffusion model, we solve it differently for a Gaussian mixture model and so on, but the problem that is going to be solved is the following. Okay, now let us look at an example for the latent variable model, which is from classical machine learning theory. Let's look at an example. From classical ML. So this is just to drive home the point of how elbow optimization is used. So an example is a Gaussian mixture model or a GMM. A GMM is also a latent variable model. Gaussian mixture model. So as I said earlier, a GMM is a latent variable model with discrete latent space. So Z is discrete, which means that Z can take one of m values. Now P theta of x, which is the model in a GMM, is given by the marginal of the joint distribution between x and z. So this is the definition of any latent variable model with discrete latent space. For a GMM, we have this P of x to be equal to, we have j equal to 1 through m, P theta of z equal to j times P theta of x given z equal to j. So now we can write the joint distribution between two random variables in terms of the marginal times the conditional distribution. This is the definition. So I've just used this definition of writing the joint distribution in terms of the marginal and the conditional here, okay, and written a mixture model this way. Here in a Gaussian mixture model, now P theta of z equal to j, which is a distribution on the latent variable, is taken to be some alpha j, and the conditional distribution of the data given the latent variable taking the value j is made to be a Gaussian distribution with a particular mean mu j and a variance sigma j. Okay, this is the definition of a Gaussian mixture model. So what happens is P theta of x, which is the latent variable model in the case of a GMM, is given by j equal to 1 through m alpha j times a normal distribution over x given by a mean mu j and variance sigma j. So this is why this model is called a Gaussian mixture model. That is, the likelihood of every point x is given by a linear combination of multiple Gaussian distributions. Okay. Now for every latent variable z taking a value j, so we have a particular Gaussian distribution. So now what are the parameters of this model? So this is a Gaussian mixture model or a GMM. Now parameters of a GMM, what is that we need to estimate in a GMM? So we have our theta, which is a set of parameters, to be alpha 1, alpha 2 through alpha m. So we need to estimate all of these alphas. We need to also estimate mu 1, mu 2 up to mu m, and we need to estimate sigma 1, sigma 2 up to sigma em. So these are the set of parameters that one needs to estimate. Now, since X is in some d-dimensional real space, okay, we have every mu j is also in d-dimensional real space, because we are talking about vector valued Gaussian distributions, and we have every covariance matrix is in the d cross d space, because it's a d by d matrix. Alpha j's are bounded between 0 and 1, because they represent the probability of a discrete random variable, which is the latent variable. And we also have that if you sum them all for m, this would sum to 1, because again this is denoting the probability mass function of a discrete random variable, therefore they should sum to 1. Okay, so this is the definition of a Gaussian random variable, and we need to find out all these parameters by the elbow optimization. So that is the goal. Okay, now how do we do that? So goal is to estimate theta via elbow optimization. This is a latent variable model, so we want to estimate theta via elbow optimization. So how do we do that? We want to get our theta star and q star that would maximize j theta of q, which is the elbow, and this optimization is over theta and q. Okay, now how do we do that is the question. One of the ways to achieve this is via the above optimization problem. The above optimization problem can be solved iteratively by optimizing for theta and q iteratively, one after the other. Okay, so what is done is that while we need to optimize this objective function with respect to theta and q simultaneously, that cannot be done. One of the ways to do it is to come up with an iterative algorithm where we first optimize this with respect to theta by keeping q as fixed, and we optimize with respect to q by keeping theta as fixed. So we do it iteratively. Okay, so here is the iterative algorithm to do that. So algorithm, what we do is that for, let's say t is 1 to some capital T, which is the iteration number. So what we do is we first find q t plus 1, which is the estimate for the latent posterior at the t plus 1 estimate, to be the maxima of the elbow. Okay, rather let's just define the terms before we go to the optimization. Let theta t and q T represent the estimates at iteration T. Right, we can randomly initialize that, and let us denote theta T and Qt as the estimates at iteration T. So the algorithm is the following: that you just start arbitrarily, and for t equal to 1 to capital T, which is the iteration number, we first keep theta a constant and find the corresponding q, the next q, by keeping the theta a constant. Okay, then with theta T a constant, so then we find the next best theta star, okay, let us write this, theta star T plus 1. So this optimization is with respect to q, and we'll find the next best theta by keeping q to be fixed at qt plus 1, with qt plus 1 being a constant. Okay, so that's all. So we alternatively find out the optima for q and theta by keeping the other constant. Okay, so this is an algorithm that is prescribed for optimizing elbow, and this algorithm is called the expectation maximization algorithm. Maximization, abbreviated as the EM algorithm. Okay, it can be shown that this particular algorithm, let me just write that, can be shown that EM ensures that the likelihood function that we find out at the t plus first iteration is at least equal to the likelihood that we have found at the tth iteration, right? So I'll not show the proof here for the want of time. So what can be shown is that the likelihood function, okay, that we would want to optimize will not decrease if we find the theta and q in this particular manner using the EM algorithm. Okay, yeah. So while this will not guarantee that our likelihood would increase when we do this, it can be guaranteed that the likelihood would never decrease. Okay. Now the question is, how do we solve these optimization problem, which is finding out q star t plus 1 and theta star t plus 1? Turns out, so for GMMs, EM for the Gaussian mixture models, turns out for a GMM, EM can be done in a deterministic manner. It can be done easily. So first we find the q star, so q star t plus 1, which is the maxima of the elbow with respect to q. This can be shown to be equal to the posterior of the latent variable given data. Okay, so this is a you can, I mean, please take this as an exercise and do that. One can show that if you want to maximize this evidence lower bound that we constructed with respect to q, the best p theta, so I'll just write that, can be analytically shown that the best q of z given x that optimizes elbow is simply p theta of z given x. Okay, so this can be shown analytically. Okay, so I will again, please take this as a homework. It can be nicely shown. So now for a GMM, while optimizing the elbow, what we need to do is that given a particular theta, we need to find out ut plus 1. Okay, so that is given by, we know that it is given by p theta of z given x. So what is p theta of z given x? Use the Bayes law. It is p theta of x given z times p theta of z divided by p theta of x. So this is the definition according to the Bayes law. We have all of these for a GMM, right? So p theta of x given z is a normal distribution at mu j and sigma j as the parameters, and p theta of z equal to j is simply sigma alpha j divided by, so what is p theta of x in a GMM? It is given by j equal to 1 through m, and we have p theta of, okay, so this is, let me just write it. So p theta of x, which is equal to p theta of x, which is equal to sigma p theta x given z times p theta of z. This is over z. Okay, this is the definition anyway. So which is given by x at mu j and sigma j times alpha j, right? So we know at the tth step, so this would be at p theta t, and all of these are at the tth iteration, which we know, because that is how we are solving the iterative algorithm. So one can easily find out what q star of t plus 1 is, right? With this particular q star, the theta t plus 1 can be simply solved by differentiating this elbow with q being equal to qt plus 1. So this is solved by the above is solved by differentiating j theta of qt plus 1, call it q star t plus 1, with respect to theta. So theta here is, we know that theta here is alpha, mu and sigma, and solving for them, that's all. So this is simple optimization using the gradients made to be 0 and solving for theta, that's all. Okay, I will skip the algebra. Anyone interested can simply take this, write down the j theta as the definition that we have given, differentiate that with respect to alpha, with respect to mu, with respect to sigma, and then find out what the best parameters are, right? So now this is the expectation maximization algorithm, which is an iterative algorithm to find q and theta for a Gaussian mixture model. Okay, so one result is that the expectation maximization algorithm will ensure that the likelihood will never decrease, and expectation maximization algorithm can be used for models like GMM, because finding out a q star, the optimal q star, which is the posterior, latent posterior given a theta, can be solved in a deterministical or an analytic way, because we know all the constituent distributions. Okay, yeah, so for interested audience here, if you recall what the k-means clustering algorithm is, where given some data points, we would first assign each of the data point. We start with an arbitrary cluster centers. We assign all the data points to the given cluster center, and we recompute the mean and we reassign. So recomputing the mean and reassigning the mean and doing doing the procedure iteratively is nothing but the expectation maximization algorithm, and one can theoretically show that a k-means clustering algorithm is an asymptotic case of GMM, where the variances of all these Gaussian mixture mod component Gaussians that we have approaches a diagonal variance, a diagonal matrix with zero variance. Okay, that can be shown. Anyway, so now the matter of the fact is that optimizing elbow for a latent variable model is feasible using the EM algorithm, as long as we can find p theta of z given x. Okay, let me write that down. Elbow can be optimized in a latent variable model, or rather for a latent variable model, using the EM algorithm provided p theta of z given x can be computed. Right? Why is this important? Because the EM algorithm involves optimizing for q and theta alternatively, and the optimal q that would maximize the elbow is given by p theta of z given x. And if the model permits that we can find out p theta of z given x using the Bayes law, which is possible in the case of GMM, then EM algorithm can be used to find out the parameters of a latent variable model. But the thing is, suppose for a latent variable model, p theta of x given z cannot be computed, cannot be estimated, then EM fails. Right? Because there's no way to find q star. So now the question is, how do we find a latent variable model? How to learn a latent variable model for cases where p theta of z given x is unknown. I beg your pardon, I think I made a mistake here. This should be p theta of z given x, not x given z. P theta of z given x is unknown. So this is the question that we would be taking up in the subsequent modules, where we will see how to learn a latent variable model for the cases where the distribution p theta of z given x cannot be estimated. Right? So why is this important? This is important because if we restrict our models to classes such as GMMs, okay, which have a nice deterministic form, then it becomes restrictive in the sense that they can only model so many classes of data distribution. So now if we want to make our p theta of x, which is the model distribution, a little more generic enough, in those cases there's no need, there's no guarantee that p theta of z given x can be computed. Now if p theta of z given x cannot be computed, then expectation maximization algorithm cannot be applied to find the parameters for a latent variable model. Therefore the question is, how do we come up with algorithms to learn latent variable models where p theta of z given x is unknown? Okay, that is the question that we are going to take up, and the neural network models such as the variational autoencoder or the diffusion model precisely tackles this question by approximating these distributions using neural networks. Okay, so we will look at how to build a neural latent variable model using VAEs in the upcoming modules. Thank you.